Okay, we're going to get into some real problems and also some derivations. And these are all based on the principles that we learned in the last video. So in this problem, this is a fairly common physics problem in this unit. We have a disk that is rotating. Okay, in this case, it's 6 kilograms at 10 radians per second. And we have a second disk that is not rotating at all. So its angular velocity is 0. And then this disk is dropped onto this disk. Now, when we say dropped, we're going to more like just place it on there. I drew it up high so that you could see it. But we're not going to deal with energy in terms of the collision. So we're only dealing with conservation of angular momentum in this problem. Now, there's a second part to this problem, which is the energy of the inelastic collision that occurs. So there is heat produced due to the friction that makes this thing start to spin more slowly. But that's in the next unit when we deal with rotational kinetic energy. So for right now, what we have is a disk. It's going to land on this disk and it's going to spin more slowly. And the question is, find the final angular velocity. So the first question that we can ask are there any net external torques on the system? And so no, there's no net external torques on the system. And what does that tell us? Well, that means that L of the system initial equals L of the system final. So what am I saying by saying this? I'm saying we can use conservation of angular momentum. So we can set this up like this. Sum of the angular momentum initial equals sum of the angular momentum final. And what do we have here? Well, we have disk 1, which we're going to say is I omega initial. But disk 1 is not rotating, so that's just 0. Then we have the second disk, which we're going to say I omega, I'm going to call that disk 2 initial. And then that's equal to I1 initial, final, times omega final, omega 1 final, plus I2 of the second disk, omega 2 final. Now, think about it in this problem. They're going to land on each other, and then they're going to be going the same angular velocity. So this is very similar to the problems where a block comes and hits another block and they move off together. They have the same final velocity, so we factor out the mass. What are we doing in this problem? We can factor out the omega. So this ends up becoming I omega 2 initial is equal to I1 plus I2, and then that's just going to be omega final. Well, what do we have for the first one right here? Well, we have 1/2 mr squared because it is a solid disk, and that's going to be times that omega, and omega 2 initial, which is 10. And then that's going to be equal to 1/2 m1r1 squared plus 1/2 m2r2 squared. And then that's all times omega final. And we have a half in each term, so we can get rid of those. And then we just plug in our numbers, which are 6.5. We have to convert from centimeters to meters, times 10, and that 0.5 is squared, is equal to 2 times 0.2 squared, that's the radius of the smaller one, plus 6 kilograms, times the larger radius of the larger object squared, and all of that times omega final. And when you do the math on that, your omega final comes out to 9.5 radians per second. So not too crazy of a problem, but a very important one to know how to do. Here's a tough problem, and in this one, we're not going to put numbers in. We're also not going to do it as a derivation. I'm just going to set it up so you see how to do it, and then we'll do another one later with a ball and a rod, and we'll put all the numbers in, or actually we'll do it as a derivation. So here's the situation. We're in space. We have a ball that's traveling along like this, and it goes into a little cup that's on this disk. Now, in actuality, we would have that cup be down in the center of the disk, or not in the center of the disk, but in the outside edge of the disk. But I'm just doing this so that you can see it. So this ball goes in, it's initially not rotating, and then it's going to start to rotate. And the question is to find the velocity of the center of mass after the collision and find the angular velocity after the collision. So in this problem, we have no net external forces, so we can use conservation of linear momentum. We have no net external torques, so we can use conservation of angular momentum. Now, here's the first tricky part. Once the ball goes into the cup, it's going to start to rotate, but it's not going to rotate about the center. It's going to rotate about the new center of mass. So if we look at this diagram right here, we have the old center of mass, and we have the ball, and that's going to create a new center of mass, and the ball disk system are going to rotate around that point. So how do we do that? Well, we use our old formula xcom to be able to find that, or it will be given in the problem. So once we know that, that's going to help us to be able to find the r that we need in conservation of angular momentum. But in terms of linear momentum, it's a much easier problem to solve. All we have is the momentum of the ball as it comes in, and then we have the two masses that are stuck together solving for the velocity that they move off at. Now keep in mind that that velocity is not the velocity of the center, it's the velocity of the center of mass. And then finally we have the angular momentum. Now the ball has angular momentum, but what's our origin? Well, to choose our origin, the best point is to choose the point that it's rotating around. So that is going to be this new position right here, this r value. And the only way we can get that r value is by finding the new center of mass. So you have to do that first before you can find this r. Once we know that r, then we need to put in I omega for the final, because we have this new object. I'm just calling it I new. It's the moment of inertia of the ball disk system. So what is that? Well, that's going to be the sum of the moment of inertia of the ball and the disk. So we sum those up, and then we put in our r that we found before, and we can solve for omega final. All right, this is the last problem, except instead of being in space, it's a disk that has an axle drilled through it. Now what that means is that once this ball comes in and hits this little cup and they start to spin together, they're not going to spin around the new center of mass. They're going to spin around the axle. The axles force a point of rotation. So there's a few things that are different about this, but the setup for the problem is the ball's moving at 20 meters per second, it's 2 kilograms, the disk is 5 kilograms, has a radius of 0.5 meters. And the first thing that I want to get into is, does the axle produce torque? Now in most of these problems, the place to choose your origin is the point of rotation. So if we choose this to be Q, the ball exerts a force on the disk in this direction. So the axle exerts a force in this direction, but that force is at radius 0. So the axle produces no torque. There is torque on the ball and there is torque on the disk, but there's no torque here. However, is linear momentum conserved? Well, there's a net force on the system due to the axle. So because there's a net external force, linear momentum is not conserved. So no. Is there a torque on the ball? Well, let's see. The disk pushes on the ball at a radius r, so yes. Is there a torque on the disk? Well, the ball pushes on the disk at a radius r, so yes. Is there a torque on the system, like a net torque? Well, there are no net external torques. Remember, this does not produce torque. So therefore, the answer is no. There's no net external torque on the system. So therefore, is L conserved? The answer is yes. Well, if L is conserved, then what can we do? Well, we can say the sum of the angular momentum initial has to equal the sum of the angular momentum final. So we have our ball that's coming in, that's r cross mv. R is going to be the distance from here out to here, so that's the radius of 0.5. And then we have, after that, we have I of the ball, eyeball, times omega final, plus I of the disk, times omega final. But remember that they're rotating at the same angular velocity after the collision, so we can factor out I ball and I disk. So that just gives us r cross mv is equal to, factoring those out, the ball acts as a point particle, so that's mr squared, plus the disk acts as a solid disk, 1/2 mr squared, and then factoring out the omega, it looks like that. So what do we have? Well, we have our 0.5 radius, our mass is 5 kilograms, and our, it's the ball. We're dealing with the ball here. The ball is 0.5 meters away, 2 kilograms at 20 meters per second is equal to, and then we have the ball at 0.5 away, plus 1/2 the disk, which is 5, and that has a radius of 0.5 squared, and all of that times our omega final. And so when we do the math for that, you end up with omega final is equal to 17.8 radians per second. This problem is instructive because of the idea of what happens with angular momentum, and you'll see that in just a second. So we're dealing with space. This could also be a rod on a frictionless table, and the ball comes in and hits it. So the ball comes in, hits the rod at the center of mass, bounces back at -2/3 the initial velocity, and the rod moves off at some unknown v com that we want to know. So the first thing that we have to say is there a net external force on the system? The answer is no, so linear momentum is conserved. So we can do sum of momentum initial equals sum of momentum final, and we have m1 v1 is equal to negative m1, and then that's going to be v1 times 2/3. And it's negative because it's in the other direction. And then we have m2 v com. So that's what we're solving for. And we just do a little bit of algebra, bring this over. And when you do that, you get a v com of 5/3 m1 v1 over m2. Now, the second question was, what's the final angular velocity? So there are no net external torques on the system, so we can say that angular velocity initial is going to be equal to the sum of the angular velocity final. But think about this. The ball comes in, if this is our point of origin, that's our point Q, then the radius is 0 for that. So our initial angular velocity is 0. So that's going to be equal to the angular velocity final, which also has radii of 0. So that's going to be 0. So there's no angular momentum involved in this problem at all. So the final angular velocity is just 0. Okay, we're going to make things a little more difficult. This time we're in space again. These problems can also be set up with a rod on a flat frictionless table, and ball comes in and hits it. But it's not going to hit it at the end. It's going to hit it at L/6 from the end. So we can break this up into chunks of sixths as we do that. And the ball's going to hit, it's going to bounce off. It's going to come back at -v/2. Then the rod's going to move off and spin. So two things that it's going to be doing here. It's going to be translating. In other words, the center of mass is going to be moving in a straight line, but it's also going to be rotating. So the question is, find the velocity final of the center of mass, and then find this angular velocity final as well. So we've been through this multiple times, so I shouldn't even have to say this again, but there's no net external forces, no net external torques, we have no hinges, anything else, so we can use conservation of linear momentum, conservation of angular momentum. So let's go ahead and do conservation of linear momentum first. So we have sum of the momentum initial equals sum of the momentum final. And what do we have coming in here? We have mass 2 comes in at velocity v. This isn't moving, so it has no linear momentum. Then they crash into each other, and we have m2 bounces off at -v/2, so that's the ball, plus m1 of the rod times v com. And then all we have to do is rearrange this with our fractions, and we get a v com, adding that over to the other side, of 3/2 m2v, that's the initial velocity, over m1. So what about the conservation of angular momentum? Well, that's a little bit more tricky. So we've got angular momentum initial equals sum of the angular momentum final. And what is this? Well, we've got the ball coming in at r cross mv. Remember, we use this when we're dealing with point particles. Is equal to, and then we can do r cross mv again, plus then the rod is not a point particle, so we define that as I omega. And now we can start to put our numbers in, but we've got to be careful. Because what is r in this case? Well, r is the distance from here to here. So that's 2/1/6, or that is 1/3 of L. So we can put in our 1/3 L times m2 times that initial velocity it comes in at. And then we have our second r. This v is minus. I'm going to bring that out to the front here. So that becomes 1/3 L, again, m2 times v/2, because it comes back at half the speed, plus I, in this case, is a rod spinning about its center of mass, which, if you remember from the center of mass unit, is 1/12 ml squared. And all of that times omega final. And once you do the math on that and deal with all the fractions and everything, you get 6 m2v over m1l. Okay, in this one we are not in space. We have some gravity acting down. This is a fixed hinge. So if this is the ceiling, we have a rod connected to this hinge, and this bar is free to swing up. So ball comes in, hits it at its end, and then it bounces back at 1/4 of its velocity, and the bar swings up. And the first question says, find the velocity of the center of mass of the bar immediately after the collision. And the second part, find the angular velocity that's of the bar after the collision. Well, the center of mass of the bar is right there, and we want to know how fast, right after the collision, what's that velocity, what's that v-com. Now, the problem with this is that we can't get this v-com until we know the angular velocity of the bar. So there's no way to do part A without doing part B. So what's the angular final velocity after the collision? And by the way, the reason that is because we can't do conservation of linear momentum. And you should know why, and that's because there's a net external force on the system by the hinge. So let's go ahead and get the angular velocity after the collision. We can do this because there's no net torques on the system. So that's going to be sum of the angular momentum initial equals sum of the angular momentum final. And we're going to have the L times m1v1, because where is this hitting it? Well, it's hitting it the length of the bar away, so that's our r in this case, is equal to, and then we have L, and then that's going to be m1 minus v fourths, because that's the speed that's coming back at, also at length L. And then we have plus the I omega of the bar. Now, of a bar spinning about its end, that's 1/3 ml squared. So 1/3 ml squared, and then that's times our omega, which is what we're looking for. So now we can bring this quarter out here and do our bring this over to the other side, and we end up with, after doing the algebra, 15 fourths m1v over m2l. So now that we found the angular velocity of this bar after the collision, and keep in mind, as it swings up, it's going to slow down. So that's why it says immediately after the collision. So right after the collision, how fast is this point moving? Well, we have to do rotational kinematics to figure that out. We can do v equals rho omega of that. So that's going to be v com is going to be equal to the distance to that center of mass, which is going to be L over 2. And then what are we going to sub in for that? Well, we're going to take this 15 fourths and bring that in for omega. So that becomes 15 fourths m1v over m2l. And our L's will cancel, and we can just rearrange that a little bit. And that is going to become that 2 times the 4, that's going to become 15 eighths m1 over m2, all times that initial velocity v. This is a great problem because there's so much going on, and if you can follow this, then you're doing great. What we have here is 2 masses that are connected by a rod of length L. The rod is so thin that its mass is negligible, so we're not going to deal with the mass of the bar. And then we have another mass that comes in and hits this. You can think of this as like a clay ball, and it sticks to it. And then what's going to happen? Well, once this ends up hitting, it's going to change the center of mass. So the center mass of the bar is right here. But then when it hits, it's going to move the center of mass of the bar over to here somewhere. So the first thing that we need to do is figure out where this new center of mass is. And the way we can do that is with our xcom formula, which is m1x1 plus m2x2 over m1 plus m2. Well, what's our origin? We have to choose an origin. So let's choose this point right here. And then if that's our origin, then we have m1x1, that becomes 0 because it's at the origin, plus m2, well, that's going to be these 2 m's stuck together, so that's going to be 2m, over the sum of the mass of the system, which is 1, 2, 3. That's 3m. Whoops, I made a mistake. x2 times L because this is L away. So the m's will cancel, and we're left with an xcom is equal to 2/3 L from the left end. So that's important. So this distance right here, that's going to be 2/3 L, or we can say that this distance here is 1/3 L. Either way, and that's important when we go to solve the next parts. Okay, conservation of linear momentum isn't so bad. We can just do sum of the momentum initial equals sum of the momentum final. And we're going to do that for the ball and the rod. So the ball is mv naught, and then these two masses are stationary, so those don't matter. So that's just 2m times 0 is equal to, then the momentum of the system, mv, that's going to be 3m v final. So our masses will cancel, and then we just solve for vf, and vf comes out to be 1/3 of the initial velocity. Okay, now we need to, and by the way, I'll just say that, that's this. That's that. That's a v-com right there. Okay, but we haven't dealt with the rotation, because as this translates through space, it's also rotating, and it's rotating around this point right here. So what is that new angular velocity? Well, we have a problem, because when we do that, this object, what's the moment of inertia of this object? So we have to go out of our way to do an additional step just to find I before we can do conservation of angular momentum. So let's go ahead and do that. So to find I, I'm going to call that I new. This is the new moment of inertia after the collision. So we got I ball left, that's going to be the ball at the left end, plus I of the two balls on the right. So what is that? Well, I new is going to be equal to mr squared, that's the ball on the left, plus 2 mr squared. Now, what's that distance to that center of mass? Well, for I new, for the ball on the left, how far away is it? Well, it's 2/3 L. And for the two balls on the right, that's going to be 2m. How far away are they? Well, they're 1/3 from the new center of mass. So when we do the math on that, we end up with I new is equal to 2/3 ml squared. Now that we have the new moment of inertia, we can do the conservation of angular momentum. So that's going to be our sum of our angular momentum initial equals our sum of our angular momentum final. And then we can do R cross mv is equal to I omega. And this is going to be the whole thing because we found the moment of inertia of the three balls all at once. So that R is going to be 1/3, so that's 1/3 L times mv is equal to the new moment of inertia that we just found, which is 2/3 ml squared omega final. And we just rearrange, we cross out one of the L's, and that gives us an omega final of v naught over 2L.